Right, so yeah, I would like to start by thanking the organizers for the invitation to take part in this very interesting conference and to present here. I would certainly have preferred to go in person to Warsaw, especially because I enjoy Polish food so much, but yeah, it's nice that it's happening anyway in spite of the current conditions. Right, I will talk about the work we do in my group on high accuracy investigations of properties of heavy elements. And before I start, I'd like to introduce myself a bit. So I work at the University of Groningen, which is in the north of Netherlands. You can see it on the map, quite far away from Amsterdam. And you can also see my research group here. I have 6 PhD students and a postdoc in my group. So at the moment, it's quite active. What we do, generally our research focuses on using state-of-the-art methods from computational chemistry to address fundamental problems in physics. And some example of this is our activities in the field of search for new physics with low energy precision measurements. So experiments on atoms and molecules that search for physical phenomena beyond the standard model, such as violation of fundamental symmetries or search for variation of fundamental constants. We also do slightly less exotic things, for example, high accuracy predictions of spectra and properties of heavy and superheavy atoms and highly charged ions. So this has to do with the regular spectroscopy, so to say. And most of the work that we do in the group is carried out in collaboration with experimental teams. So it's mostly entangled in experimental context, which means that we need to try to achieve very high accuracy, and we also try to be able to set uncertainties in our predictions. Today I focus on the last of these topics, so high accuracy investigations of heavy and superheavy atoms. And I will start with a short motivation of this field of research. Yeah, so we're interested in heavy elements, in particular in transuranium elements, atoms that do not exist in nature, which are produced artificially. Within this group, we have also transactinide or superheavy elements with the atomic number larger than 103, which are even more challenging for production. And these atoms, they're produced either in nuclear reactors or particle accelerators. This is a very challenging field of research. We also work on highly charged ions, and in terms of computations, highly charged ions are actually similar to heavy elements in that relativistic effects become very important. Right, so a field of research of heavy elements is very active. There's a lot of different contexts. So a lot of research is carried out on nuclear properties, decay measurements and so on, but there's also many atomic, spectroscopic and chemical experiments. And the motivation for the later, there's many reasons to do this work. So in particular for newly discovered, newly produced atoms, one wants to get some information about them, assign them eventually in the periodic table. Generally, study of heavy elements provides us with new information about behavior and trends in the lower part of the periodic table, where we know that relativistic effects become very important. The studies are also very nice benchmarks for theory. For example, contribution of QED effects, which becomes very large in heavy atoms, can be disentangled from our other effects, and different theories can be tested. Experiments, spectroscopic experiments or chemical experiments can also be used to extract other properties of interest, for example, nuclear structure from hyperfine structure measurements. And yeah, if we go back to the context of search for physics beyond the standard model, also we know that heavy elements experience enhanced sensitivity to such phenomena, so they're very promising systems for such experiments. Right, so while this, yeah, it's an active field, there's a lot of experiments done, but these measurements are very challenging, and there is a number of issues. So First of all, we have low production rates. This becomes very difficult for super heavy elements, where production rates can go down to a few atoms per month. These elements are radioactive and short-lived. Again, for super heavies, we're talking about lifetimes of minutes or seconds for the most stable isotopes. This problem is less crucial for lighter of the heavy species. If we have to produce our elements artificially in nuclear reactors or in particle accelerators, that means that we need a nuclear reactor or particle accelerator. It means our experiments require large facilities, they become very expensive, and they become also logistically very difficult. So these are all the challenges related to this type of research. And this means that, so first of all, because of the expense and involved logistics, if one attempts to perform measurements, it's best that the attempt is successful, which means that one needs to develop very special experimental techniques for this kind of experiments, so very fast, very sensitive techniques, but also theoretical support becomes necessary for success of such experiments, because basically anything that can help is very useful. Right, so what can theory do in this context? We're talking about atomic molecular theory. Yeah, so theory is necessary at all stages of the experiment. Yeah, starting with providing reliable predictions for planning the measurements. This means, as an example here, we can provide the predictions of transition lines, which allow spectroscopists to focus, to avoid broad wavelength scans and to focus on a certain range of wavelengths, which is very helpful if one is trying to perform the measurements on unstable short-lived isotopes. So this saves a lot of time and makes the measurements possible. Theory can also provide parameters which are needed to extract some data from measurements to extract the properties of interest. Example shown here is the hyperfine structure, which is measured. What is measured is transition frequencies. And by knowing some theoretical parameters, one can extract nuclear properties from these frequencies. For example, nuclear quadrupole moment or nuclear dipole moment. Also, we can provide predictions for comparison with the new measurements as confirmation of the new results. Or conversely, we can look at this another way, that new experiments come up with measurements which allow very stringent tests of existing theories of their performance and predictive power. As is an example here where the experimental measurement of some transition in nobelium is compared to previous theoretical predictions. Right, also because of knowledge of what's happening inside the atom, knowledge of the wave function and the atomic properties, we can interpret the measured results. We can explain why some properties of the observable properties are what they are. And finally, also as theorists, we're not limited by practical considerations, stability or availability of an atom or whether a property can be measured or not. So it gives us some freedom to perform calculations where no experiment is yet possible. I like to give the example, as example, extended periodic table of Pekka-Pico. And this kind of research, of course, on one hand, it can be useful for future experiments. On the other hand, there's just many things, many systems that we cannot yet study experimentally. And this is the only way to get some information about them. So, yeah, but regardless of what we do with our theory, regardless if it's used in experiment, in particular if it's used in experiment, but also for theoretical, purely theoretical work, in order to be useful and reliable, our predictions should be based on high accuracy calculations. And in particular, this becomes important in experimental context. We should also be able to somehow estimate uncertainties on our predictions if we want these results to be used in measurements. Right. This means that the choice of computational method becomes very important. I guess everyone here has seen this kind of computational landscape. Before, the three axes stand for the three main parameters that determine the quality of any calculation. We have relativity, electron correlation basis set, and we need to find ourselves on this landscape. So what we want to do, we want to be able to perform high accuracy calculations of properties of heavy and super heavy elements. And this means that, in order to do this, we have to treat relativity and electron correlation on highest level that we can, which points us towards the computational tools that we should use. So we start with the treatment of relativity. We cannot, for this type of systems, we cannot use relativity as an add-on or perturbation. We have to work in relativistic framework, so we work within the Dirac-Coulomb-Bright Hamiltonian. We also can add higher order QED corrections on top of our results if higher accuracy is needed. And what is also important, in particular for hyperfine structure, is to model the nucleus as a finite object, not as a particle, not as a point-like particle. Right, so going back to the landscape, we're somewhere here for this calculation. So we go beyond the perturbative methods and we work in a four-component framework. Second parameter, which is very important, is treatment of electron correlation. In our case, we choose one of the most powerful methods, relativistic couple cluster. I think it's the best one can do for heavy many electron systems. We have two variants of this method at our disposal. We can use the single reference couple cluster for closed shell systems, simple systems. This method is suitable for ground state and lowest excited states. If we want to treat open shell systems or more complex systems, we will use the multi-reference Fock-based couple cluster. And in particular, the nice feature of this method is that it can provide us with both ground state and excited states, many excited states in a single calculation on the same level of accuracy, which is perfect for spectroscopic studies. And then depending on what we want to calculate, what kind of systems we want to look at, we'll select one of these methods or use both in complementary manner, if that's useful. Right, so we're somewhere here. Final parameter is choice of the basis set. We use Dial's basis sets, which are suitable for relativistic calculations. We use a large size basis set to augment them by high angular momentum and diffuse functions when needed, and try to extend them to convergence. Right, so by default, we're somewhere here. So we try to go quite far on all three axes, which provides us with a very powerful computational method, but also quite expensive. And this slide, I have the summary of what we can, what we cannot do, and the advantages and drawbacks of our methods. So we can treat heavy and super heavy atoms and small molecules, highly charged ions. We're limited to small molecules, of course, due to computational expense. So we can reasonably work with 2 to 5 atoms, more or less. We can calculate a whole spectrum of properties, energy properties, organization potential, spectra, electron affinities, and so on, but also molecular structure, hyperfine structure parameters, parity validating coupling constants, and basically if a new property is needed, we can also implement it. So the method is very versatile in this sense. The nice feature of this approach is that its couple cluster is quite transparent and we know what we include, which means that we can improve our results systematically and we can even attempt to evaluate uncertainties. And generally, the accuracy that we expect by default from this kind of calculations is on the order of tens of milli-electron volts. So not as great as the previous talk, but these, of course, are much heavier systems. There's also some drawbacks. First of all, as I said, this method is expensive computationally. And presently, the Fock-based couple cluster method is limited to systems with up to 2 valence electrons or holes, which of course means that we cannot treat any system we're interested in. Well, the first limitation is inherent to the nature of the method. We're actually there's work carried out in my group to overcome the second limitation and extend the Fock space couple cluster to treat more complex systems. All right, so in terms of software, we use two different packages. We use the Tel Aviv program for atoms and for Fock space couple cluster calculations, and we use the Dirac package for molecules, for properties, and for a single reference couple cluster. All right, so yeah, I'll spend the rest of the time on presenting some applications of these methods. And I have selected applications which perhaps do not represent the full variety of different systems that we study, but each of these applications was selected to represent some kind of a computational aspect of our work, or some decisions we have to make, some new developments we have to do. So the first example has to do with getting the optimal accuracy out of our methods. Second example is I will present a scheme which we kind of implemented to evaluate uncertainties in our predictions. The first two examples deal with atoms and with energy properties, electron affinities, and ionization potentials. Third example is a molecular example, and I will show a different kind of property, the hyperfine structure constant. So just to show also the variety of applications. All right, we start with the first example, the ionization potential and electron affinity of gold atom. The point of this work was to investigate how far we can go with the method. So I mentioned earlier that the accuracy we can expect from our calculations is on the order of tens of millielectron volts. And the question that we can ask is, can we actually do better? Or how much better can we do? And if we go back to the computational landscape that we saw before, basically trying to do better corresponds pushing further on all three axes of our method. So including higher order effects for all three computational parameters. And we tried to do this. Our study system was gold. The properties were ionization potential and electron affinity. And we started the study with trying to get rid of basis set incompleteness. So the first thing we did was worked on extending our results to complete basis set limit. And all the numbers I'm going to show now are already extrapolated to complete the basis set limit. And I will present the numbers for ionization potential. Exactly the same study was carried out for electron affinities. I will show also the result at the end, but just to focus on less numbers. So these are results extrapolated to basis set limit, IP of gold atom. We see that for coupled cluster with single and double excitations, we have a large error compared to experiment of 0.1 electron volts. This is the experimental value. Switching on perturbative triples actually overshoots the mark, and we get an error which is similar in size, but with an opposite sign. So CCSD parenthesis T, which is considered to be the golden standard of computational chemistry, it does not do so well for gold, unfortunately. So we see what we can still improve. We have treatment of electron correlation. So far we stop at perturbative triple excitations. What we wanted to do is see the effect of higher order excitations. We did that using the MRCC package of Kalaya and the relativistic wave functions. And we see that already going from perturbative triple to full triples cuts the error by half. So this is a very significant contribution. Quadruple excitations have some effect, and and we see that at quintuple excitations we're more or less saturated. So this is where we stop, both because adding further does not seem to have an effect, and because of computational expense. All right, so we have improved. So obviously the result is improved, but we still have quite a bit of error compared to experiment. What we still can look at is the effect of relativity. So this is, this result is Dirac-Coulomb, uses Dirac-Coulomb Hamiltonian, which is relativistic for the one electron term, but not for the two electron terms. What we can do is we can add the bright contribution, which again reduces the error quite significantly. And finally, we also add the QED corrections, the self-energy and vacuum polarization. These were calculated with the model lamp shift operator of Shabayev within the coupled cluster approach. So these are correlated calculations. Finally, adding this QED part brings the error down to just a few millielectron volts, to 3 millielectron volts, which is the accuracy that we try for. So we're trying to achieve a few millielectron volt accuracy. As I mentioned earlier, the same calculation was in parallel carried out for the electron affinity. Same effects were added up and similar final accuracy was obtained, again, less than 2 millielectron volt error. And it's important to stress that we're not trying to match the experiment. We're not trying to fit the experimental value. What we do is we try to add all the higher order effects that we can in a balanced and careful way. And doing that allows us to achieve this accuracy. So this is a universal prescription that works for many different types of systems. Here I have a graphical representation of the different effects, how they affect the accuracy. And this work was published a few years ago. And since then, we actually used the scheme that we developed in that paper for other calculations where we need as high accuracy as we can achieve. All right, so this is for the first example. Second example has to do with also high accuracy calculations, but also error evaluation or uncertainty evaluation. Here we worked on electron affinity of astatine. So this was a joint effort of theory and experiment to measure electron affinity of astatine and predict it theoretically. Astatine is the most rare naturally occurring element. There is very, very small amounts in it on Earth. But astatine, which is produced artificially, is used in targeted alpha cancer therapy. And this is why we want to know as much as we can about its chemical or atomic properties. So the reason why it was important to measure its electron affinity is to do with being able to predict its reactivity and what kind of compounds this atom will form in our bodies because of how rare it is. It's not well investigated. These measurements were performed at Zolde at CERN using laser photodetachment spectroscopy. We carried out our calculations before the measurements with a double aim of providing reliable predictions to guide the measurements and for comparing with the experimental result after the fact. Right, so here again, we wanted to get as high accuracy as possible. So we used the scheme which I introduced for gold, for astatine. We carried out the same calculation for its lighter homologue iodine, where experiment was available, where we can use the experiment to evaluate our accuracy. Right, so we add the same corrections as before. You can see that the effect of this higher order contributions is much, much smaller than for gold because of different electronic structure. On the other hand, if you compare iodine and astatine, the magnitude of the different contributions is quite similar, which is, of course, a good sign since they're homologues and we expect them to behave in a similar way. Yeah, so for iodine, our result is in good agreement with experiment. We expect similar accuracy for astatine, but then, then we got asked actually what is our uncertainty. And there's not really any formal way to estimate uncertainty for theoretical predictions. It's a very complex topic. What we did in this case is we use an ad hoc scheme where we followed the logic of our attempts to increase the accuracy. Basically what we do, so we go as far as we can on each of these three axes.
Anastasia, you have just a few minutes left. So
I'm almost done, yes. Yeah, so we go, thank you. We go as far as we can on each of these three axes. And of course we cannot, and there are parts which we cannot evaluate, we cannot calculate because of computation costs or other considerations, but we can estimate the order of magnitude and use this order of magnitude to set the uncertainty on our results. We do that using computational study. We do it for every axis separately. So for example, on the relativity axis, we're missing high order Q defects. We assume them to be smaller than vacuum polarization and self-energy, and we assign the corresponding uncertainty for these elements. As we do the same for higher excitations and the basis set incompleteness. And assuming the different effects to be independent of each other, we end up with this total uncertainty of about about 15 millielectron volts, which is dominated by basis sets incompleteness, which makes sense for electron affinity, which is extremely sensitive to basis set effects. Right, so we add this uncertainty to our predicted results. And in the meanwhile, the measurements were carried out. We can then we could finally compare our prediction to the measured results. Yes, this is the new experimental value. So we can see that for both elements, so for iodine, but also for astatine, where the prediction was done blindly, we are in excellent agreement with the experiment. We can also see that our error bars seem to be over-conservative. So this is another conclusion from this work. Yeah, so basically the outcome of this theory experiment collaboration is the knowledge of the electron affinity of astatine. We find that it's the lowest for halogens, but highest among the rest of the periodic table. And also some chemical properties can be extracted from known electron affinity and ionization potential. Right, this work was done by a PhD student in my group, Yan Gu, and was published very recently in Nature Communications. Right, last application, very quickly, is another type of property, magnetic hyperfine structure constant in barium fluoride. This is a new implementation.
Anastasia, but there is almost no time, so just try to squeeze.
How long do I have, sorry?
1 minute, so maybe two minutes, but just.
2 minutes, yeah. I mean, that's one slide, basically. Yeah, so we test out the new implementation. We use barium fluoride as a test system because there's a very accurate experiment known. We do this similar estimate of errors as we did for the atoms. We calculate the parallel and perpendicular hyperfine structure constants. And we see that the uncertainty now mostly comes from higher excitations rather than basis set effects, which means that for different properties, we need to do this estimate separately. We cannot use the same rule of thumb. And if we can compare our results to experiment, we see that we're again in excellent agreement with the measurements, and our uncertainty is again over conservative. Right, so also was published very recently, another student from my group, Pihaza. This brings me to the end of my talk. So yeah, I have shown some applications of relativistic couple cluster, method that performs very well for heavy many electron systems. And we can achieve very high accuracy by including high order corrections, and we can even evaluate the uncertainties, but we're now working on a more rigorous scheme for estimating these uncertainties. And this method also allows us to very easily work with experimental colleagues, which of course makes it very nice for us. I'd like to acknowledge my external colleagues on this work, and I would like to also thank you for your attention. And
so, Anastasia, thank you very much for a very interesting talk. Let me ask if there are any questions, because I have quite a few. Are there any questions? Okay, so let me then start from my questions. Anastasia, you have estimated a percentage of your QED effects.
Yes.
The same, it was the same amount as the total value of the QED.
No, higher order QED effects. So
You estimated higher order QED effects by 3 MeV, which is exactly the total value of QED. So I would say it is a little bit, to me, it sounds like an overestimation. Because I would estimate high order QED to be smaller than the QED, than the estimation of the QED from the Shabayev potential. I would say maybe 10%, maybe even a few percent, but it's maybe one of the reasons that you overestimate the uncertainty. Another one, there was a long-standing discrepancy for the hyperfine splitting in barium. And the resolution was that the magnetic, I don't remember which isotope, if it is exactly the same which you studied. But for one or for a few isotopes, the magnetic moment was incorrect because of the mistake in the calculation. So if you want to compare your theoretical predictions for the molecules involving barium, please check what is the correct value of the barium magnetic moment, because it is a problem by itself.
Okay,
in fact, it was 2 or 3 years ago, Shabayev has written a paper about the about changing the value of barium magnetic moment, but I don't remember which isotope. That was in fact the experiments, because there were long-standing, because in GSI they want to measure hyperfine splitting and they cannot find the line, and they cannot find the line because the magnetic moment of barium was incorrect, so they cannot resolve the line, find the line. So it was rather interesting. I would say for me, it was a very interesting talk. Now I see your background because you collaborate with, you were involved in this in this package. I don't remember the name of this package, but with these Israeli co-workers, I also have Russian co-workers, so you are very well grounded with this. So thank you very much. Maybe there are, again, further questions. So maybe then I will ask you the question: how you represent the basis function? Do you use the Gaussians or you use
Gaussians?
Gaussians.
Yeah. Okay.
So now I have the answer. Very good. So are there any further questions? If not, let me thank you once again